So I would like to tell you about what we have uncovered about the boson whose discovery allowed us as a community to receive the Nobel Prize in Physics last year. So this is a one-to-one scale reproduction of the CMS detector, and this is about 1/6 of the people who work in CMS. Now, I was thinking what happened is that 17,600 hours ago, in a conference 17,000 kilometers away, we had the first episode in 2012 of a new particle. Now, it was, just to recap, it was the 5 sigma day. There was 5 sigma in CMS, 5 sigma in Atlas. Everything looked standard model-like. Now, what we said was that we needed much more data in order to be able to figure out what exactly this boson was, and the LHC delivered those data. So we got in total something like 30 inverse femtobarn delivered, but it came with a challenge, a very big challenge of being able to do precision physics in the presence of 20 simultaneous collisions on average. And you have at the bottom one of the events. It was actually in a special run, but this is what it looks like to have 78 proton-proton inelastic interactions simultaneously. And we were able to reconstruct them. So there was a very large amount of work that was done in order to cope with this, both online and offline, in order to be able to present not only my results on the Higgs, but all the results from CMS that you'll be hearing about in the remainder of the plenary sessions today. So these precision measurements actually build, we are on the shoulders of giants, the people who thought about and pushed through with building these very large detectors, which have very, very accurate measurements, and those who have endeavored to go beyond leading order into next to leading order into next to leading order, performing calculations of standard model expectations, which can then be summarized in this sort of plot that covers 6 orders of magnitude of measurements that we have performed in CMS. Now, just a brief word how standard model Higgs has come to be at the LHC. There are 5 main production processes. The largest by far is gluon fusion, which proceeds through a loop of top quarks, B quarks, well, anything that has color. So for instance, some BSM particle which has color can also run on those loops. And then there's vector boson fusion, which has these 2 associated quarks going out, which are collinear with the beam, or almost collinear. So they go forward, so it has a very distinctive feature. And then there are associated production modes with W and Z bosons and with TT bar. In particular, this production mode, TTH, is the only way we have at the LHC to look directly at the coupling between the Higgs and the top quark. Again, because in gluon fusion, it's a loop. We don't know exactly what's running in the loop. It might be top quarks. It might be something else. On the way out, the Higgs bosons decay foremost into BB bar pairs at the mass of 125 GeV. We actually have, if the Higgs boson has this mass, we are in a really sweet spot where we can have access to almost all of the decay modes. You can see down to gamma-gamma or to Z-gamma, it's more or less where they are the largest. If we would be 10 GeV up or 10 GeV down, your life would be harder in order to figure those out. Then this is again a place where there is another loop, because photons are massless. The decay of the Higgs boson into diphotons, here at the bottom left, is mediated by a loop of top quarks or W bosons. Any charged particle will do the trick, so it could also again be another BSM particle. Now, for those of you who were here at the parallel sessions, there was a wealth of results presented in 15 talks and 4 posters. I am unfortunately unable in the time that I've been allotted to cover all of these results, but I'll just try to pick on some of the pieces that are in, well, this rather oversimplified big picture, the drivers of what knowledge we can extract regarding this Higgs boson. So this brings us to this year's episode, the Higgs boson strikes again. CMS, since ICHEP 2012, has actually put out its 5 main results. They are all published or submitted for publication. So last October, we had the associated production of Higgs to BB bar and a V boson, so Z or a W. The mass resolution in this channel is not great. I mean, these are jets, B jets, so you have something like 10%. Then in December, we had the Higgs into WW analysis, which covers different production channels. Here, the presence of 2 neutrinos from the semi-leptonic decays of both Ws makes the mass resolution to also not be fantastic. It's only 16%, but there's a very large yield, and this actually allows you to have a very large expected significance. In our case, the expectation was almost 6 sigma. At the same time, in December, we also put out the Higgs to ZZ to 4 lepton analysis, and here the mass resolution is excellent. The yield is a handful of events. You can actually know them by name, but the background is also very low. And actually, this had one of the first nicely precise measurements of the Higgs mass. Then later in January this year, we had the tau-tau result out. As Marumi mentioned, the tau-tau channel is a difficult beast. It's, taus are not leptons in the usual sense of lepton. They can decay in all sorts of manners and ways. The mass resolution, because of the presence of the neutrinos in the final state, ranges between 10 and 20% in case it's a leptonic decay of the tau or if it's an hadronic decay of the tau. And we actually, our result had a 3.2 observed significance of 3.2 sigma, which was the first evidence for the coupling, direct coupling of the Higgs boson into fermions. And then we actually took together the BB and tau-tau results, and also in January put out a combination providing strong evidence of about 3.8 sigma for the coupling, direct coupling of the Higgs into fermions, and this was rather well received by the community. Then more recently, in May, we have a study that was published on the off-shell production, and this Marumi has already explained to you. I'll come back to it in more detail. And finally, just during this conference, we have submitted for publication the Higgs to gamma-gamma final run 1 full data set analysis. Gamma-gamma has an excellent mass resolution, and Marumi has also showed it's really difficult to nail down all of the aspects related in order to get the best photon energy resolution. So this is new, and I'll bring you through this. This is one of the Higgs into gamma-gamma. The photons leave these big deposits in the electromagnetic calorimeter. This is just one candidate. We never know if this is a Higgs boson or not, but many people just like to point at this and say, that's the one. Well, we don't know. This new analysis builds upon the final calibration of the CMS electromagnetic calorimeter for the run 1 data. This was a tremendous tour de force, which was brought together by a very large team of people. We have also understood many, many details of what is going on in the data, in particular, the evolution of the noise, the intrinsic noise of the detector in the electronics, and we actually simulated this in a differential way with time, the effect of out-of-time collisions and how this pile up, this extra energy affects the reconstruction of the energy of the photons that you're interested in, and last but not least, a much more detailed and accurate understanding of the material which is upstream of the electromagnetic calorimeter, where you have interactions that will degrade your energy resolution. Then another thing is that we had much more time to look carefully into describing the energy scale uncertainties associated with the photons from the calibration with Z to E decays, because electrons and photons in the electromagnetic calorimeter are very similar. Then there are some differences which introduce some uncertainty, but we've understood the scale, not the resolution, in much more detail. Well, also the resolution. Then another big gain came from going into 25 exclusive event categories that address all the known production modes, or the 4 main production modes of the Higgs boson. And finally, we have a new technique to model the background, the smooth background under the gamma-gamma Higgs peak, which considers multiple functional forms simultaneously in the likelihood. So at the bottom, you see that these three changes, these three improvements, are all more or less have the same sort of impact on the expected sensitivity since our last preliminary result back in 2013. So the significance that we observe in Higgs to gamma-gamma is of 5.7 sigma. We were expecting 5.2. And we usually look at this in the weighted mass distribution. So there's a very nice peak coming out. And one of the things that you can do when you have all of this precision is to actually have a precise measurement of the mass. So we have now a measurement of the mass, which is, well, it's still statistically limited, but there was a lot of work that went into the systematic uncertainties, and I'll just take you through this. So first you start with something which is 0.05 GeV from the calibration itself, and then you want to go from the scale of objects from the Z decays, where we do the hard work because it's a standard candle, we know everything about the Z, to go into the scale of the Higgs boson. And this we do in data by taking high PT Zs and look at what is the linearity when going from the Z mass scale to the Higgs mass scale. And here there is an extra uncertainty of 0.1 GeV. And then the next thing you want to do is to check the differences between electrons and photons. And this is done in simulation. We look at the comparison between data and simulation between electrons and photons, so it's a double differential correction. And for this, we find that the uncertainty that is induced in the mass measurement is also of 0.1 GeV. Okay, so then if you look at the signal strength, so the relative signal strength with respect to the standard model, the final result is about 1.14 times the standard model. You will see that the theory uncertainties are by now larger than the systematic uncertainties or all other systematic uncertainties, which are not theoretical in nature. But of course, we are still statistically dominated. But in the future, for run 2, this will become a topic of great concern. Now, once we have all of these results, we can start making combinations. And the first thing, the same way as Marumi showed, the first thing that you combine is the high-resolution channels into a mass measurement. So we do this combination by floating the individual signal strengths so that, you know, the yield, there's no assumption on the yield, so you just let the yields float. And when you combine the two measurements, we get 125 plus or minus 0.3. And we see that the compatibility between the two measurements in CMS is at the level of 1.6 sigma, and it has the opposite sign as in Atlas. So, you know, one sees it like this, the other sees it swapped. So when you combine, everything will cancel out in a way. So there was the 124, there was the 126. We actually know that it's the 125. I think what they never thought is that it's, you know, plus or minus 0.3. But there could be other things. And there could be the 500, the 1400, the 800, the 2300, or the 600. So we have to look for these. And one of the ways to look for these is not the direct effect, not just direct searches, but look for the effects that they might have on the properties of the 125. So for this, we can do the full combination of all of the results. And we also included the TT bar searches, which are just these three particular analyses here at the bottom. Now, this represents more than 200 channels to be combined, and I'm not counting the number of bins. This is just number of exclusive classes of events, and more than 2,500 floating parameters in the fit. So this is, it's quite a tough cookie for Minui to swallow, and we have to do a lot of careful massaging and making sure, for instance, that we are not getting something which just got stuck in a local minimum. So the signal strength that comes from the combination is by chance, 1.00. The remarkable thing here is, please don't look at the central value, look at the uncertainties. If you look at the uncertainty breakdown, you see that the statistical uncertainty and the theory uncertainty are more or less at the same level. So there's now, between now and the first results of run 2, is the time to figure out how to reduce the theory uncertainties so that we can keep them matched. So this is the result when you group it by the dominant decay in each of these groups. And so you have BB, tau tau, gamma gamma, WW, and ZZ. And now if you turn it around and you group the channels by the tag, so when you ask for 2 jets, you will be dominated by VBF. It's not just VBF, but it will be dominated by VBF. And what you see is that the TTH tagged is above the standard model by about 2 sigma. Now, we know exactly why this is. It's because there is one particular analysis of same sign dimuons with TTH production, which is actually pulling the result. So this is one of the things that we'll need more data or better observables, better analysis to understand if it goes up, down, if it stays there and the uncertainty shrinks, et cetera, et cetera. It's one of the things to look forward for the run 2. Now, if this was just, what experimentalists define, I take my events and I put them here, I take another set of events, I put them there. Now we can try to work on pseudo-observables. So the model and the underlying model of what is the coupling of the Higgs to this particle or that particle. So these are the standard model particles, and you have a gauge sector of 3-level couplings which are related to electroweak symmetry breaking. I mean, if this is the Higgs boson, and we know that it is a Higgs boson, it's related to electroweak symmetry breaking, it has to have a special relationship with the Z and the W, like custodial symmetry, etc. Then you have the photons which are mixed. I mean, because in the loop, remember, there's the top and the W. And then you have the Yukawa sector. So these are all the fermions. And I know the gluon is not a fermion, but it's effectively a quark loop because it's tops, bottoms, charms that go in that loop. So the gluon couples to the Higgs, let's say, effectively through fermion loops. And of course, you know that there are up-type particles, so you can look at the top and the charm together, and you know that there are down-type particles like the tau and the B, so you can group these things in these many different ways. So that's why we did the framework together with Atlas and with the theorists in the LHC Higgs cross-section working group. This is, I'm not going to go through all of the details. You basically see something divided by something in the standard model equals kappa squared. So some of them have 3-level terms, like kappa this, kappa that. Others, you can actually decide, for instance, for gluons, you can assign an effective kappa and say, I'll scale gluon fusion by this value. Or you can actually resolve it, and this is done in NLO-QCD and leading order electroweak accuracy. You can resolve the gluon fusion loop into its top part and its bottom part and the interference. Same thing for gamma gamma, same thing for Z gamma, same thing for then the partial width of the decay into gluons. And then the other thing you probably have to assume is that there's CC bar and SS bar and mu mu, and if you're not measuring these, instead of sticking them to the standard model, you can say, well, these should scale, SS bar should scale with BB bar, CC bar should scale with the top, and mu mu should scale with the tau. I mean, they are all cousins. Finally, there's one aspect that you need to consider is what do you do with the total width? So one way of dealing with it is to say the total width will just scale according to the scaling of the partial width, or you can just say, I don't know what's going on, and I'll just scale the total width by itself. And this you can do, for instance, by scaling the total width of the standard model, as you would expect, and adding something which is a branching fraction into invisible or undetected particles. And we'll see some results also on that. So the first model that we usually test is called, it's this kVKF. You have one kappa for all fermions and one kappa for all vector bosons. And you see here that in the combination, the gamma-gamma result has the power to distinguish between same sign, kappa V, kappa F, or flipped sign. And this is a very nice feature. You can see that the channels come together on the top quadrant, and then they all spread apart on the bottom quadrant. And then if we look just at the top quadrant, you can see very nicely how they all are fitting into that region, and that the standard model diamond is very, very well inside the 68% confidence region for the combination. Now, there are many ways then of breaking off these kappas, and these are just the summary of 6 of the benchmark models. The take-home message is everything which should be compatible with 1 is compatible with 1, and then this extra branching fraction which should be compatible with 0 is compatible with 0. So no news here. Now, since we had these final results, which have quite a bit of power, we decided to try the most general benchmark that was proposed, less than 2 years ago, and we thought it was going to be impossible somehow. And this benchmark then has a specific parameter here, which is this kappa gz, which is kappa g times kappa z divided by kappa h. So this also floats the total width. And then everything else is measured in terms as a ratio. So kappa w over kappa z, kappa z over kappa gluon, et cetera, et cetera. And you see that everything is compatible with 1, except for what would be kappa top over kappa gluon. And this is, again, because of the excess that we see in TTH production, which is driven by the multi-lepton analysis. So another way of looking at this problem is what Marumi was saying. We can try to set a limit or we can measure these couplings not on the peak, not on shell, but at the rest of the propagator. And the rest of the propagator is quite large because of a lot of threshold effects. You see here there's this very long tail. It does not decay directly as a Brout-Englert, but there's a lot of yield there to be exploited. And if you look at the propagator for this process, there are 2 limits. There's the limit when you are on shell, and in this case you have, for instance, in the denominator, you have the total width over here. And there's a limit where you go far off shell, and then the total width does not enter the game. It becomes just the coupling to the initial state and the coupling to the final state. And if you take the ratio, you get something which allows you to make some inference on the total width itself. So in CMS, we took 2 channels, ZZ into 4 leptons, and ZZ into 2 leptons and 2 neutrinos. And for the 4 leptons, there is a very complicated bidimensional analysis in which one of the dimensions is a discriminant between the gluon fusion production and the QQ bar production of Z pairs. And in the 2 lepton 2 neutrino, it's much simpler. It's just the transverse mass shape inclusive in all jet bins. And what we see is similar to Atlas, although we saw it sometime before, that the combination is, in this case, 5.4 times the standard model width, smaller than. This is a 95% confidence level limit, whereas we expected 8 times. Okay, now something which is new, that was presented for the first time at this conference, is the characterization of the spin 0 amplitude in the decay into di-bosons, di-vector bosons. You can write this amplitude in a rather general way. You have this term here, which is the standard model one. So if this is 1 and everything else is 0, you recover the standard model expectation. Then you can add something which is, higher order kinematics, Q squared proportional. And then you have the A2 terms, which have CP even couplings. And then you have the A3 terms, which have CP odd couplings. So, and then these come in many flavors, because you have the part which is VV, the part which is V gamma star, and the part which is gamma star, well, Z gamma star, and then gamma star, because, photons and Z's are just the 2 sides of the same coin. And we went and did a lot of these fits. This is computationally very intensive, and it requires a lot of understanding of the observables, because in the ZZ to 4 lepton final state, you have all of the kinematics available to look for these things. So you can reduce the 8 dimensions that you have available, the 8 degrees of freedom, into 2 or 3 in order to make some fits. And then you can do scans of these anomalous coupling fractions, which are expressed as fractions of the cross sections associated to each of the anomalous coupling terms. And so here you have, for instance, the CP odd versus the CP even versus the CP odd. And in this case, for real phases, and you see the standard model is that cross, and the best fit is on the cross. And you can then, instead of assuming real phases, you can float the phases. And in that case, you have this scan over here where the standard model is, again, the bottom left point. And the best fit is somewhere along this axis, but it's well within the 68% confidence level. Because once you float the phases, you lose a lot of the power, but you get a better understanding. Now, another type of analysis that we do for characterizing the spin, in this case for J bigger than 0 sort of states, is specific hypothesis tests. So there you see the log likelihood ratio, the test statistic that we use for this sort of tests. In yellow, the distribution in yellow is what you expect under the 0+ hypothesis. And in blue, in this case, is what you would expect this test statistic to look like under the 1- hypothesis. So that would be a pseudo vector. And the arrow represents the observation in the data. So you see in this case that the data looks more standard model-like than the standard model would say. We take this into account by using the CLS technique, where instead of just taking the tail of the blue distribution, et cetera, et cetera. You can ask the details later. So then we perform this many, many times for many, many hypotheses. And you basically have this plot rotated and here. So each of these points represents that arrow. The orange bars represent this distribution, and the blue bars represent this distribution. And all of these are excluded at more than 99.9% CLS. So then the question is, are there any other models, things that we haven't seen before and we should look for? So one of the things that Marumi also mentioned is the direct search for invisible Higgs decays. In this case, you tag the events using these objects. So in this case, VBF, you have the quark jets. And in ZH, you have, in the case of CMS, we do a combination of dilepton and Z to BB bar. And then you can set very competitive limits for low mass dark matter in the Higgs portal models. So you see here, these are the direct search experiments, and these are the limits that we can set using the Higgs as a tool. Then another thing is to understand whether this is one Higgs or if there are so many more Higgses. And in the minimal supersymmetric model, there are 5. 3 which are neutral and 2 which are charged. And then we took based on the standard model analysis, but looking for extra B tags, because in the MSSM you get a lot of production of gluon fusion into BB phi, and extending the analysis up to 1.5 TeV. If you do this sort of search in terms of the MSSM parameters, MA and 10 beta, you can see that you had an expected limit which was around here, and the observation is a bit not as excluding. And you have then that this is compatible with the presence. If you inject the standard model Higgs boson that we've seen, you see that the observation is compatible with that signal injected. So this is something to look forward to, more analysis of this type to try and look for more Higgs bosons. Another way of looking for weird things is to look at the flavor couplings of the Higgs boson. This is one of the things that will definitely come up in the future, and we have an analysis which was first presented at this conference for the decay of the Higgs boson into muons and tau leptons. So this is a lepton flavor violation. And you see here, this is for the mu tau E, where the tau decays leptonically, and the mu tau had, where the tau decays hadronically, for 0 jet events, events with 1 jet, and events with 2 jets. And there is a slight excess in a few of the categories, which allows us only to set a limit of 1.6% at the 95% confidence level, whereas we will expect to set a limit of 0.75%. Nevertheless, this is a great result, because this is the picture for the Yukawa anomalous couplings, the off-diagonal Yukawas for the Higgs boson. And you see that the limit that we set now is 4.4 times better than the one which was set before from tau to mu gamma experiments. And well, you never know. It might be that the Higgs flavor sector holds surprises, and that's why we cannot set a better limit. Now, finally, one aspect of Higgs physics that will be very important for run 2 is TTH, because we really need to figure out how this particle couples to the top quark, because the top quark is so massive, it might actually have a special role that we do not yet understand. So there is a new analysis that was first presented at this conference of doing TTH search with Higgs decaying into BB bar using matrix element method. And this is very nice because it has a reduced dependency on the TT plus BB plus EC heavy flavor modeling, which you see, this is the best category where you identify one of the W's into 2 jets, so you reconstruct the W mass. And then this one sets a limit of 7.1 times the standard model. If you combine it with the other categories, you get a limit which is 3.3 times the standard model. Now, if we start looking beyond run 2, at the end of run 2, we know that we'll have a very good improvement on the measurement of the signal strengths into the different Higgs decays. So these are two different scenarios for extrapolating the uncertainties. In green, nothing changes. We just assume that we'll have the same uncertainties we have today, experimental and theoretical. The red is the opposite end of the spectrum. You assume that the experimental systematics go down with 1 over square root of the luminosity, and that our theorist colleagues are able to slash their uncertainties by a factor of 2. That would be really great, both things, on the effort on the experimentalists and the effort on the theorists. And then for the high luminosity LHC with the 3000 inverse femtobarn, we expect to be able to find Higgs decays into mu mu at better than 5 sigma. And is there some hope to get to the Higgs self-coupling? And for that, we've started taking, the first steps, baby steps. There's an analysis looking, in this case, for radion from warped extra dimensions. This would be something that decays into 2 Higgs bosons. And then you look at the signature where one goes into BB and the other goes into gamma gamma. And this is basically just the first step towards being able to have a comprehensive set of measurements of 2 Higgs production at the LHC. So this brings me to my summary. CMS has closed a major chapter in the characterization of this Higgs boson, and it has published or submitted for publication the main 5 channels that are used. We've shown at this conference the first combination of these final run 1 results, and I believe that we have the most precise Higgs mass measurement of 125 plus or minus 0.3. Up to now, we've seen no new Higgs physics beyond the standard model. Not yet. And we continue to turn all stones. There are some surprises, but we make hundreds of measurements. If you see a couple which are 2 sigma away, it's natural. It's called the Luke-Alcer effect. And we are not just found this particle, we are now measuring this particle. And this brings me also to my conclusion. We've just started, and there is a very, very long way to go, where we want to go from measurements which are at the order of 10% uncertainty to differential distributions, because that's where we are going to understand a lot of the physics in the kinematics, to go from scene, which is the characterization in the particle data group review of particle physics for some of these decay channels, into real 1% precision measurements of the Higgs boson, to go from limits on rare things. I didn't mention many of the things like Z gamma, LL gamma, so it's basically gamma star gamma. We want to go from limits on them to actually measuring them and have 5 sigma observations. And we need, as a community, I believe, to reduce theory uncertainties. There's a lot of effort ongoing. It's every time I mention N3LO, people tell me, yes, and then you write down all the diagrams, which as if it's some sort of, I have to write on the blackboard all the diagrams. But we need this in order to explore the full potential of the LHC and its upgrades. Now, I was looking for the next episode, and so when I Googled ICHEP 2016, yes, I found, I believe, the right ICHEP 2016, but I also found an ICHEP 2016 exactly with the same title in Zurich, and in the same website, one in Paris. So this is what experimentalists would call fakes. But okay, regarding the ICHEP 2016, it will be 18,000 hours from now in a conference 7,000 kilometers away, and I hope that it will be the return of the LHC, and who knows? We might have answers to those questions. Thank you.
Thank you very much, Andre. Okay, questions for Andre?
There are questions on the right side.
Yes, here on the right. 2 questions.
That was a nice talk. You mentioned a few times that the signal strength for TTH is rather high. Just eyeballing, it looks like about 4 plus or minus 1.5 in the WW channel. Could you just comment on the dominant systematics and also whether the results in the different flavors, E mu and mu mu, are consistent with each other?
So let me pull up the slide on that. So this is the channel which is foremost pulling it. I mean, it's called WW because we needed to group the channels, and the largest contribution to this analysis of TTH decay with decays into multileptons is from WW decay. Sorry. So there was a very, very long list of cross-checks performed before we put this out, and we've actually not found any wrinkle on this thing. So it's either a statistical fluctuation, and that's the way life goes, but this is the distribution where you see it. And we've done the analysis in other ways, and that's how it's coming out.
But is that result systematically limited, and if so, what is the dominant systematic on it?
Good question.
It's coming from TT bar background, maybe? Or?
I don't know. It probably is, because you see that, well, no, it's not systematically limited. The statistics here is very small. It doesn't make sense that it is systematically limited.
Thank you.
Both you and Atlas have very precise Higgs masses. Can we expect that you could combine those at sometime in the near future?
Yes. I see spokespeople nodding. The only question is how near. I mean, it's as near as we can make it. But I mean, at least from the CMS side, we were missing this piece, which was the gamma-gamma analysis, and that is now out. So from our side, we can proceed. I believe that from the Atlas side, we can also just proceed. And we've been discussing, actually, it's something which has been prepared in the last several months. We have been preparing to actually do that.
If the Higgs was mixing with another scalar like the CP odd Higgs of the 2X Dalbert model, how well can LHC measure that mixing? Like if the Higgs was decaying, say 1%, 0.1%, 0.01% in a CP odd way, is that possible to measure?
So I think that the answer to your question is somehow in these very colorful plots. I'm sorry if I need to move around a lot. Yes, this sort of plot. So this is basically the fraction you see here in FA2 versus FA3. Let's imagine that the couplings are real, because there are many degrees of freedom in this. But these represent the fractions of the part that goes into the CP odd and the CP even anomalous couplings. So we can do this sort of measurement. Now, whether we can get it to 1% or 10%, there are some extrapolations of these analyses to 3 inverse femtobarn that we have presented elsewhere. And it's definitely one of the main things. I mean, that's why we chose to present it here, because we know that now that it's spin 0, we need to figure out if it is a mix of states or not. But there are also other ways of looking into that, which will come out soon.
Okay, let's thank Andre again. And we move now to the theory. So next